Hello everyone, my name is Anton Rigner, and today I will present you the paper Radar-based Situational Awareness for Industrial Safety Applications. This is joint work with my colleagues Philipp Sommer and Martin Zlatanski at ABB Research, Switzerland. In recent years, we've seen a growing demand for collaborative robots. Such robots can increase productivity of factories by operating safely in close proximity to human coworkers. There are several methods to protect humans from potential dangers of industrial robots. For example, by limiting the actuator force or physically fencing off the robot in safety zones. However, safety fences are costly and they require more space around the robot. Dynamic speed and separation monitoring is a more flexible approach where we use sensors to have a virtual fence around the machine or a robot. Based on continuous monitoring of the distance between the robot and human operator, we adapt the speed of the robot and behavior based on the separation between the two. For such a system to work reliably and safely, however, it is important that we can distinguish between the movements of human coworkers and other robots or machines on the factory floor. We have developed a custom platform based on two off-the-shelf sensors, a radar sensor from Texas Instruments and a 2D LiDAR sensor from SICK. The LiDAR sensor is mounted below the radar transceiver, which allows us to map the LiDAR measurements into the coordinate system of the radar and vice versa. Measurement data from these two sensors are then fed into our processing platform. We use the LiDAR data to detect targets in the proximity, while the output of the radar is further processed to perform target classification. The output of our system are the positions of the detected targets together with their corresponding classification as human or non-human. The radar sensor operates at 77 GHz according to the frequency-modulated continuous-wave principle. In such a radar, the frequency of the transmitted signal is linearly increased during the duration of a so-called chirp. When the emitted signal hits a target, the signal is reflected and can be detected by the radar receiver. The resulting output of the receiver circuitry is a superposition of several low-frequency signals, which frequencies depend on the distances of the corresponding target. The sampled signals of several consecutive chirps are then stored for further processing in the digital domain. First, we perform a fast Fourier transform along a chirp, the so-called fast time axis, to obtain the spectrum of the signal, which contains the different targets. Next, we perform a second fast Fourier transform over the chirp dimension, the so-called slow time axis. This results in the range-Doppler map, where the targets are separated by their distances and velocities. In our system, we combine LiDAR and radar data to perform detection and classification. We detect the targets using the 2D contours provided by the LiDAR, as it is challenging to detect targets using radar only in indoor environments with many reflecting surfaces. The corresponding section of the range-Doppler map from the radar is then used as input for target classification. We can clearly see that the range-Doppler signature is changing over time, and it will look different depending on the target and its movements. Our system takes into account the temporal changes and the characteristics of the range-Doppler signatures to perform target classification. On this slide, we show an example for each of our target classes, part of our dataset which we recorded in an indoor environment. At the top, we see contour data from the LiDAR. Based on the difference between the current measurement and a previously recorded reference, we identify the position of the target. This is shown by the red dot. At the bottom, we see the range-Doppler maps, based on the radar data. The corresponding section representing the target is indicated by the vertical lines. In order to develop classification algorithms and to evaluate their performance, we have used our sensing platform to collect a dataset containing measurements of 4 different target classes. The first 2 classes represent a human that is either standing or walking. Furthermore, we have 2 non-human targets. One is an ABB single-arm Yumi robot that is performing continuous pick-and-place movements. The last class is an electrical fan, which mimics the behavior of a rotating machine. We have developed 3 different classification algorithms based on machine learning. The first one being a support vector machine with handcrafted features. The second one is a classifier based on convolutional neural networks. And the third classifier combines a convolutional neural network with a long short-term memory unit. The classifier based on support vector machines employ an RBF kernel to introduce nonlinearity to the system. The classifier is trained with handcrafted features, and they're inspired by classical radar signal processing literature. Some examples of the features that we use are statistical properties of the signal, such as the variance of the velocity of a target, approximations of the linearity of the motion, and the maximal value of the velocity in the radar Doppler signature. Furthermore, we make use of the cadence velocity diagram. This is the result of a third fast Fourier transform along the distance axis on the radar Doppler map. The cadence velocity diagram indicates which frequencies, if any, are present in the radar Doppler map. Some examples of these frequencies could be the swinging motion of the arms, the cadence of the legs while walking, or the breathing motion of a human being. Our second classifier that we train is based on convolutional neural networks, which are widely used for image classification. The idea here is to treat a section of the radar Doppler map as an image and use it as input to the neural network. The architecture of our network consists of 2 sets of convolutional and max pooling layers with 32 filters for the first layer and 64 for the second. We then feed the flattened output into a fully connected layer to perform the final classification task, assigning a probability to each of the 4 target classes. Our third classifier combines the convolutional neural network presented before with a long short-term memory unit to capture the temporal behavior of the target. To evaluate our classifiers, we train the classifiers using cross-validation, with folds selected according to the leave one group out method. We provide the confusion matrix of all 3 classifiers to visualize their performance. As you can see, the SVM-based classifier, based on handcrafted features, achieves a total accuracy of 79.6% on our dataset. It separates samples of the human walking, human standing, and fan classes quite well, but it's not able to accurately separate the moving robot from the human movement. It could potentially be improved by utilizing other features that we did not think about. The CNN-based classifier shows a better result, achieving an accuracy of 94.3%, and the combined CNN and long short-term memory unit classifier achieves a final accuracy of 96%. We observed that treating the radar Doppler sections as images improves the performance compared to our classifier with handcrafted features. Furthermore, modeling the temporal behavior results in even slightly better accuracy, especially for the examples with the moving robot. To summarize our work, we have developed a custom multi-sensor platform to classify targets in an industrial environment. The sensor platform is able to detect targets in its proximity using Lidar. A radar sensor is then used to classify the detected targets into 4 classes, using the radar Doppler signatures of the target. We evaluate 3 different classifiers based on machine learning, with the highest performing one being a CNN and LSTM-based classifier, achieving an accuracy of 96% on our dataset. I would also like to outline potential future work towards robust classification algorithms for industrial safety applications. One could, for example, combine several sensing methods to achieve higher classification accuracy. We could integrate the classification algorithms with target tracking methods, There is also further work to maintain real-time constraints of the application. And finally, there is work to compare our method to other methods, such as only using visual cues and regular RGB cameras in different sensing environments. This concludes our presentation. Thank you very much for your attention.